Hi and welcome everyone. My name is Marco Lübbecke and I will kick off the decomposition day at CO at Work 2020. Behind me you can see the topics we will cover, which is column generation, Dantzig-Wolfe Reformulation and branch and price, and we have roughly an hour for that, and we can never cover these three topics in an hour, so let's try. Here's what I assume you to be familiar with, and I'm sure you are because you have seen the courses so far in this week here. And this is what I would like to do with you today. I would like to introduce you to two new algorithms, which is column generation algorithm and branch and price algorithm. And I'm doing this, maybe surprisingly, with the aim of expanding your modeling capabilities. I will show you why in a minute. Ultimately, we are always interested in solving integer programs, and this day here is about structured, specially structured integer programs, and the aim in the end is to solve them faster. Okay, so directly jump into one here, which is the cutting stock problem. You probably all know that one. Here's a formal presentation of it. We are given m rows, they all have the same length L, and we are given n orders of length Li. So these are integer numbers here, but this doesn't really matter. And every order has to be cut di times. So this is a demand for each order. So we are cutting the rows into orders, and the goal is to minimize the number of rows that we need to cut all orders. This is the classical textbook formulation here, already presented by Kantorovich 80 years ago. So what he did is he has a integer variable, xij, and it means how often order I is cut from row j. I have to ensure that we sufficiently often cut each order, so for each order I'm summing over all the rows and somehow often the order I is cut from the respective row. So this is the number of times the order is cut, and this should be exactly, or at least, the demand. Of course, I cannot cut more from a row than is available. So here I'm summing what I'm totally cut from one row j, and that should be not more than the row's length. And this gives me a feasible solution, but so far I cannot count in the objective function. For this, I need to introduce an additional type of variable, which is a binary one for each role, and it says whether the role is used or not. And here's the link between cutting and using. So whenever I cut from row j, I need to use row j. So this is an implication constraint here, enabling myself to count the number of rows I cut in the objective function. Okay, so this is the textbook classical formulation. Very nice. So let's look at solutions. How do solutions look like? What I did here is I'm enumerating all the possible ways how I could cut one row into pieces, into orders. So what I could do here is, well, I only cut once the first order, or I cut the first order twice, or I cut once the first order and once the second order, or only once the second order, or twice the second order and once the third, and so forth and so forth. Okay, so this gives me a large number of possibilities how I could feasibly cut one row into orders. And what I'm doing here is I encode each of these, what I call cutting patterns, into integer vectors. So for example, this vector here represents that the first order is cut once, and I do not cut the second and third orders. And when you can check the vectors here, you can see how they are defined. These are integer numbers, and they must satisfy one constraint, that I do not cut more from the row than is available. And this compact way here gives me a large, potentially very large set of all the ways I could cut one row into orders. Let's denote by AIP the number of times I cut order I from a given pattern P. Okay, so here, for example, A1P from this pattern would be 2, because I'm cutting twice the first order. And with this, I can come up with a different kind of model. So I'm basing a different integer program on this observation I just had. So I have a new integer variable for each pattern, and it says how often that particular pattern will be used in my solution. Okay, all I have to ensure is that I'm selecting a number of patterns so that in total, the total concert of them, so to speak, exactly satisfies my demand. So I'm counting how often a particular pattern is used, then I know how often a particular order is cut from that pattern. So I'm summing here in total over all the patterns how often a particular order is cut, and that should meet my demand. So this gives me a feasible solution. And now, because every pattern is exactly equivalent to using one role, so whenever I use a pattern, I have to use one role. In the objective function, I only have to sum over all the variables, because that says here how many patterns will I use. This is exactly the same number as how many roles will I use. Okay, so this is a completely different kind of formulating the same thing, the same problem. This one here gives me an integer program with many variables, because there are potentially many potential ways of cutting one role into orders. Okay, now you may ask, so why should I care? Why is it important to know that there are different ways of formulating one and the same problem into integer programs? And I would like to demonstrate you why this is important to us. I brought you one of these instances, and I would just call skip. So here on the command line, it's an older version, but this is not really important. So here is one of these cutting stock problems. It's actually a bin packing problem. It's very related. And now skip is trying to solve it. It has, I think, 200 orders, and we would like to minimize the number of roles, so the number of bins that should be used. By now you can probably read the output here. So you have the dual bound, the primal bound, the most important numbers here. We found a solution which uses 97 roles already, and we know there is, because they're integers, there is no solution with fewer than 94 roles. Okay, resulting in that gap here, and that is perfect. When the role is not too expensive, I could just stop here. I have a solution of sufficient quality. When the roles are very expensive, I might be really interested in an optimal solution, and we have 1 hour. As I said, we cannot really wait for a solution here, so I would stop this. Yes, and start GCG, which will solve the second problem I presented you. So it's the same instance I read, and I start the algorithm on that model with many variables, and you can see here it has a solution of 97 roles as well. Oh, and it stops, and you can see 96 was the optimal solution value. So we found a better solution after a short amount of time. Now you have seen it can make a huge difference in computation time when you use different models for the same problem. And you may now ask, okay, how is this possible that there are so huge differences in computation time? And if you're interested in that, stay with me. This is why we're here. So this is our agenda: some column generation, some Dantzig-Wolfe reformulation, and some branch and price. Let's start with column generation. So what we would like to do is to solve, first of all, a linear program, because these are linear relaxations of integer programs later. So we would like to solve a linear program, and we call that the master problem. It's just an LP as you're used to see it. The only difference here is that we assume that there's a super huge number of variables, so we cannot solve that. What we do instead is we just take a much smaller set of the variables, so only a subset. We do not call that the master problem, but now the restricted master problem. And this is what we assume to be solvable in reasonable time. Okay, so this is what we do. Usually we can use the simplex method for that, and we will obtain a solution. What we always get also is an optimal dual solution. That will become important in a second. So just remember, for every constraint here in the primal, we have a variable in the dual, and we will receive an optimal dual solution. And the question is, maybe we are lucky. Maybe the solution we obtain for this restricted version with a few variables, maybe that solves the problem we are originally interested in, the master problem, optimally as well. How would we find out? Well, we have to check the reduced cost of all the variables we have not considered so far. This is the only thing you really have to know from the simplex algorithm, the formula for the reduced cost. So for every non-basic variable, I can compute the reduced cost as the original cost minus the dual variable vector times the coefficient column of that variable. Okay, so here's a number, there's a number, difference is a number, and the sign should correspond to a minimization problem that should be non-negative for all the variables, and then I have proven optimality. This is a sufficient condition, and I could check this condition for all the variables I have not in my model so far. Okay, so this gives me the first algorithm. We call that explicit pricing. So pricing is the step in the simplex method where we evaluate the variables for their reduced cost and check whether there is a promising variable. What I can do is, well, I get the restricted master problem, the linear program with a small subset of the variables only. And what I do is here in this loop, I solve that restricted version to optimality. We assume that works. I get the primal and the dual solution. Then for all the variables I have ignored so far, I just compute the reduced cost. I can because I know their cost, I know the coefficient columns, I have the dual solution here. And if there is a variable I have not in my model so far, but it has negative reduced cost, I add it to my model and repeat. And I do this until I have proven by computation here that all the reduced cost of the variables are non-negative. And the only flaw here is that this step is computationally prohibitive. I cannot enumerate all the variables and check their reduced cost simply because there are too many. Instead, what we always do in optimization then, instead of an explicit enumeration, we do an implicit enumeration. So we solve a helper and auxiliary optimization problem, which we call the pricing problem. I just write it down here as I would like to minimize the reduced cost over all the variables. Okay, assume I could solve that. I would get an optimal objective function value here. And when this is negative, what I know then is that this optimization problem here produced a variable with negative reduced cost. So I would add that variable to my restricted master problem and re-optimize it. Otherwise, when I know that the minimum, so the smallest reduced cost of any variable is non-negative, then I know there is no variable of negative reduced cost, and that would prove optimality of the master problem. Okay, this is what we would like to achieve. Does not seem that we have gained much, but let's write down the algorithm this results in. This is the column generation algorithm. Again, as an input, it gets the restricted master problem, so the LP I'm interested in solving with a small subset of the variables. And I solve that restricted version to optimality, get a primal solution and a dual solution. Then I solve this helper optimization problem, the pricing problem. And when this has negative objective function value, I know I have identified a variable of negative reduced cost. I add it to my model and repeat. Okay, and this I do until I have proven that the smallest reduced cost of all the variables I have ignored so far, that is non-negative, and then I can stop. This is the column generation algorithm. Okay, let's look at an example how that could work in practice, so to speak. Let's look at the Gilmore-Gomory formulation. So this pattern-based formulation of the cutting stock problem. We have seen this so far, and let's say we initialize this model with only a small subset of patterns, wherever we got them from. Okay, so this has few variables. I can solve that one to optimality with, for example, the simplex method, and what I will get also is an optimal dual solution. So for every constraint here, for every order, I get a dual variable, okay, a value. So let's assume we are given these optimal values from the optimal solution. Then we can compute the reduced cost. So that formula that will appear over and over again. So it's better for you to memorize it if you haven't done so. So the reduced cost of one pattern is its original cost. In our model, this is always 1, minus the values of the dual variables. We got them from the solution of the restricted master problem. And the coefficient column of the variable. So remember, the coefficient columns of the variables in that Gilmore-Gomory formulation, they encoded feasible patterns, feasible cutting patterns. Okay, so this I could evaluate for all the feasible patterns, and we said, okay, an explicit enumeration is totally out of the question. So how could I do this implicitly? So how would this pricing problem, this helper optimization problem, look like? So remind you, what we want to do is we would like to minimize the reduced cost over all the feasible patterns. This is the reduced cost formula over all the feasible patterns minimized. So we have the nice situation here that we know how these coefficient columns here will look like. They encode feasible patterns, and we already thought about how that should look like. These should be integer numbers, we said. non-negative integer numbers, and they should respect this capacity constraint here. I cannot cut more from a role than its length. In the objective function, you can see this is the reduced cost of one particular pattern. So this is the original cost minus the dual variable times the coefficient column here. And if I rearrange this a little bit, so then you can see here, this is a constant minus, and what remains is a knapsack problem. Okay, so that makes perfect sense. I try to cut from a role to pack into that role items such that the capacity is not exceeded. That's a knapsack problem because I would like to have it as profitable as I can, and the dual variables here give my profits on the items. Nice. So what can happen? Two cases actually for the minimum reduced cost. So the objective function value of the pricing problem. That could be negative. And if so, then I know that the variable values of the pricing problem, they encode a feasible pattern. This is exactly how we did it. So then we could add that pattern and the corresponding variable to the restricted master problem and iterate. So this was a master problem variable with negative reduced cost. It's promising for progress, so I add it and re-optimize. Or I solve the pricing problem and the optimal objective function value is non-negative, then I know there is no feasible pattern of which corresponds to a master variable of negative reduced cost. Then I stop. If you have seen this for the first time, maybe you just pause here and skip back to the beginning of the presentation of this algorithm and repeat listening to what I just said. Here's a picture of what happened. So this is the restricted master problem. I just initialize the model with a small subset of the cutting patterns, and then in each iteration a new variable corresponding to a new pattern is added, and the hope is that the resulting model, so the restricted master problem, when I can prove optimality of the master problem, is much smaller than the original master problem I wanted to solve. So this process, for obvious reason here, is called column generation, because I'm adding these coefficient columns successively. And let me stress again, this is an algorithm for solving linear programs. Okay, good. So why should that work? So why should in the end we have any hope that we would not generate all the variables of the master problem? So one main reason is, you know from LP theory, that any basic feasible solution has as many variables as I have constraints. And constraints I have few. I have many variables, yes, but most of them are non-basic, so at value 0, so I don't need them anyway in the model. So the hope is, because we know empirically that the runtime of the simplex method linearly depends on the number of rows, that I will never ever see most of the variables of the master problem in a basic solution. Okay, so if I don't see them in the algorithm, why should I have them in the model? So that is one rationale. And the other comes from integer programming. So this pattern-based model, if you come from an integer programming point of view, you would like to compare the strength of the LP relaxations you could obtain, and that of the pattern-based model is stronger than the first one by Kantorovich, the assignment-based model. Theory will help proving this, and the pattern-based model has some more nice properties. For example, it's not symmetric, so it has nice properties, and I have two motivations, so to speak, from a linear programming point of view and from an integer programming point of view. And of course, at the moment, you have to believe me that all this is true, but once you have your own practical experience with these kind of models, you will probably acknowledge that this is the right thing to do here for certain kinds of problems. Here's another example, the vertex coloring problem. So what is that kind of a problem? You're given an undirected graph like this one here, and I would like to color all the vertices. I did this here already. The only rule is no two adjacent vertices must receive the same color. Okay, this gives a coloring. Turning this into an optimization problem is do this with a minimum number of colors. So I did this here with 3 colors, and fewer is not possible. So this is an optimal coloring of the vertices with 3 colors. There's a classical textbook model here. And when I have the set of all the colors available, I have binary variables for every vertex in the graph and each color. And the binary variable says whether that node will be, or that vertex will be colored in that color, yes or no. Then I have to ensure that every vertex receives exactly one color. I have to ensure this collision constraint. So whenever I have an edge in the graph, the two endpoints must not be colored in the same color. I have to enforce this for every color. Yes, looks tedious, but this is how one could formulate it. And this gives me a feasible coloring, but I cannot measure again in the objective function the number of colors. So I introduce a new variable for each color, a binary variable, whether I use that color or not. Here's the linking between the two. So whenever I color a vertex in color C, I must use color C, and then I can count this in the objective function, just minimizing over the used colors. This is an integer program. The optimal objective function value is the chromatic number of the graph. It's a hard optimization problem, but this is how you could solve it, at least for small instances. Okay, so let's try to do the same thinking as we just did for the cutting stock problem. Look how solutions look like. And if you look at, I can go back here to the graph. If you look at how solutions look like, you will see, for example, the blue ones here, they are not adjacent. Well, of course not. They must not. This is forbidden. So all the blue vertices, they form an independent set, a stable set in the graph. Same goes for the green ones, for the magenta ones, for the white ones, for the yellow ones, for the black ones. So each color class is an independent set in the graph. Okay? So looking from that perspective, I can just enumerate all the independent sets in the graph. There's a many, 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 but I don't care. And then I will have a variable for every independent set in the graph. And the variable will say whether I will use that independent set in my coloring solution in the end, yes or no. What I have to ensure is that every vertex appears in some of the independent sets I selected. And I have this parameter here, AIP, that says whether vertex I appears in the independent set P, yes or no. So I'm summing over all the independent sets, and each vertex must appear exactly once. Now the final observation is whenever I pick an independent set, it means I have to pick a new color. So I'm minimizing over all the independent sets I've selected, the number of independent sets. I need to partition the entire vertex set is exactly the chromatic number of the graph, which gives me a huge integer program. Many, 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 many variables, because there are many independent sets in the graph. Okay, how to even only solve the LP relaxation of this, what we call the master problem. Okay, because the many variables, we solve it by column generation. Okay, solve, that LP would give me, as we've learned, also the dual variables, one per constraint here, and I have a constraint per vertex, so I have a dual variable, one per vertex. Okay, so this is if I solve the restricted master problem to optimality. Let's say I'm starting with a small set of independent sets which are sufficient for an initial solution. So now I would like to know, do you know how the pricing problem would look like? Maybe you just press pause and think a little bit about this, skip back and check the problem definition and this master problem. And I would like you to write down how the pricing problem looks like. So maybe you did the same thing as we did for the cutting stock problem. You just said, okay, I'm minimizing the reduced cost over all these, well, let's say feasible patterns. In this case, these are all the independent sets. And this is the reduced cost formula. It's always the same. It's the original cost. It's also 1 here, minus the dual variable vector times the coefficient column of a variable. And the only question is here, how is this coefficient column encoded? So how does an independent set encoding here looks like? So that would be a binary encoding. That should be whether I take a certain vertex into the independent set, yes or no. And we already saw how we can write this down, because this was in the other formulation, one of the constraints. For each of the edges, I must ensure that I do not pick both endpoints. Okay, so this gives me here an independent set, a stable set in the graph. And this is the reduced cost formula. It's just 1 minus and then the dual variables times whether a vertex is in the stable set I should construct, yes or no. And I can put out the constant here. And then I will see that this is a well-known problem that results. It's the maximum weight independent set problem. It's a hard problem as well. Okay, but anyway, this is how the pricing problem looks like. You would solve that to check whether there is a variable that you need in the restricted master problem to get some progress that you would add, then repeat re-optimizing the restricted master problem, get a new dual solution, ask the pricing problem, and so forth until the pricing problem here says there is no independent set with negative reduced cost, so there is no variable missing in the restricted master problem. You have proved optimality of the master problem. Now let's assume we all understood this. Then the next question would be, how would we arrive at such models with this large number of variables? So you have seen two examples now. Is it creativity? Is it experience? Is it routine? Is it textbook work? What is it? And so this brings us to the next topic, which is Dantzig-Wolfe reformulation, which gives us a very systematic way of taking one integer program and reformulating it in a mechanic way, so that we will arrive at a model that looks very much like these master problems we have seen to be solved by column generation, which is why column generation will appear in this subsection here as well. So you know this result already, that there are two representations of a polyhedron. A polyhedron is the feasible space of a linear program. And you know, either you have this description as the linear inequalities or the convex combination of the extreme points plus the conic combination of the extreme rays. And what we know is there's only a finite number of the extreme points and a finite number of the extreme rays which are relevant here. So you have seen that in the very basic LP section. We will use this theorem to equivalently reformulate a linear program. So again, you're looking at linear programs. We are looking at linear programs because they are LP relaxations of integer programs usually, but so far a linear program. We call that the original model here in our context. And what we should do in the beginning is we should split the constraints into two kinds. And we will call the ones the easy constraints. So these are here the dx greater than or equal d. And the other ones are then the complicating constraints ax greater than or equal b. So that has historical reasons. Let's just say we can split the constraints into two distinct sets. Okay, so what we will do is we will take one of the sets, the easy set, dx greater than or equal d, and we will apply this Minkowski-Weil reformulation on that. Okay, so look at this here. So we have the two kinds of constraints, ax greater than or equal b and dx greater than or equal d, and we take this second set here, dx greater than or equal d. This gives me a polyhedron with extreme points and extreme rays, and I will use the inner representation. The Minkowski-Weil says that works. The inner representation to reformulate the LP. So how would that work? Well, I take the representation Minkowski and Weil says exists of that easy polyhedron. So I know I only need the set of extreme points and the set of extreme rays. Let's say I'm given these finite sets. And then can I express every x in this polyhedron as a convex combination of the extreme points. So you can see here, this makes it a convex combination, a negative combination summing up to 1, plus a non-negative, a conic combination of the extreme rays. Every x can be represented like this. Now I take this x with this representation and just substitute it in the remaining constraints. Okay, so I have the ax greater than or equal b and the objective function, and whenever there is an x here, I just substitute this expression. This happens on the next slide. So whenever there was an x here, I substitute, well, the convex combination of the extreme points plus the conic combination of the extreme rays. And so you can do this slowly here. What I will just do is some rearrangement of the variables and some renaming. For example, you can see here the cost coefficients appear here. They are multiplied against each extreme ray, and I will just give these new names because these are numbers anyway, and these are column vectors here. And this gives me what we call the Dantzig-Wolfe master problem. It is a linear program in new variables. So these coefficients here for the convex and conic combinations are the new variables now. I have the convexity constraint. I have the old complicating constraints, but now expressed in the new variables. And I have the old objective function, but now expressed in the new variables. Okay, this has many variables because there are many extreme rays and extreme points. But because this is an equivalent reformulation, this has the same objective function value as the original LP where we started from. Because of the large number of variables, such a model would need to have to be solved by column generation. And we know how to do this. We only need some extreme points and some extreme rays to initialize the restricted master problem. This is what we can solve, for example, by the simplex method. And then we would obtain a solution, but we know now what is more important is that we obtain a dual optimal solution as well. Why is that important? Because, so here's the restricted Dantzig-Wolfe master problem with just a small subset of the extreme points and extreme rays and the dual variables. And when we solve that, we need the dual variables. So maybe just go back and check that this is exactly what we want, to check the reduced cost of all the variables we have ignored so far. So for all the variables which correspond to extreme points, we have their reduced cost, which computes as always the same formula, the original cost, we know that one, minus the dual variable values, we have them computed, times the coefficient column of an extreme point, and we know that this is exactly how it looks like. And we can even here use our definitions of the cost coefficients and the coefficient columns here, that they came actually from original data of the original model. So that was the original cost coefficient times the coordinates of the extreme points. This gives me the cost, minus the dual variable vector times, and this is the original coefficient matrix, times the extreme point, and here's also a dual variable. Okay, so this is the reduced cost of an extreme point. And in the same way, I have the reduced cost of an extreme ray. The only thing is, because the variables of the extreme rays, they do not appear in the convexity constraint, they have a 0 in the convexity constraint. That's the only difference. Okay, so I can compute reduced cost for the extreme points and the extreme rays, and I'm looking for one of them which has smallest reduced cost. Complete enumeration is completely out of the question. So what we should do is, find an optimization problem which gives us as a solution an extreme point or an extreme ray of smallest reduced cost. And this is what the Dantzig-Wolfe pricing problem actually does. So here it says minimize the reduced cost expression over all the extreme points and extreme rays. Give me a smallest one. And the benefit here of this reformulation is that we exactly know how these extreme points look like in the extreme rays, because they're extreme points and extreme rays of this reformulated polyhedron here. So we just write down the constraints of the polyhedron describing it. And if you use, for example, the simplex method, you will end in an extreme point of that polyhedron with the smallest reduced cost, or in an extreme ray. And then this is exactly what we need. An extreme point or an extreme ray minimizing the reduced cost formula. Okay, this is, again, look at this. This is a linear program, so we can solve that to identify a variable which we might need to add to the master problem. 3 cases this time, not only 2. So the first case could be, this was not possible before, it could be that the pricing problem is unbounded from below. That means that we have identified an extreme ray, right? In particular, the objective function value is negative. So we have a variable corresponding to an extreme ray with negative reduced cost. And we could add the corresponding coefficient column to the Dantzig-Wolfe restricted master problem and reiterate. Solve the restricted master problem, get no dual variables, solve the pricing problem, and so forth. So that is case 1. Case 2 is the optimal objective function of the pricing problem is finite, but negative. Okay, so that means I have identified an extreme point, because we landed in an extreme point when we used the simplex method of that polyhedron here. So I have an extreme point and the objective function is negative. So that means I have a variable of the restricted master problem of negative reduced cost. So I would add it and reiterate. So here's the coefficient column of the variable I should add, exactly as the reformulation said us to do. See that there is a 1 here in the convexity constraint because it is an extreme point and it should appear. And the third case is the objective function, the optimal objective function value of the pricing problem is non-negative, and that proves that there is no variable we should add to the restricted master problem. We can stop. We have solved the master problem to optimality. And that was very fast. I know if you haven't seen that before, I really encourage you to skip back to the beginning of this small unit here and read that again, what we were just talking about. So this is how Dantzig-Wolfe Reformulation works for a linear program together with a column generation algorithm to solve it. Okay. When we're interested in a solution to the original model, we can always project back. So this is by construction the correspondence between the original and these master variables. We can always obtain an original solution from the master solution. So let's just stop here for a second. I encourage you to go back to our two examples, so the cutting stock and vertex coloring problems. And now you will see that in the master problems and in the pricing problems, we used constraints that already appeared in the original formulations. Okay, so this is not a coincidence, but when you look closely, you will see that it's not exactly the same. Somehow these formulations, they forgot about, well, the roles for the cutting stock problem and for the colors. So the independent sets, they had no colors for the vertex coloring problem. This is very common and useful, and this is called aggregation. So I will not talk about the details here, but this is what often happens. And at least looking at these examples will give you some intuitions what the connection is, and hopefully gives you some illustration how the Dantzig-Wolfe reformulation works. Because we were in a situation, which is this one here, which is a very classical Dantzig-Wolfe reformulation, when the reformulation can be applied, because you might have several independent subsystems in your model, and they are only linked by, well, what we call the complicating constraints. So for example, these here could be the constraints ensuring that every role is feasibly cut into orders. The first role. The second role is feasibly cut into orders, the last role. And I have constraints for every role, and they are independent of each other, and they are only linked by the constraints that in total I have to satisfy the demand. So this is what we often see. Okay, if you look into the coefficient matrix here of this model, it would look like this. So every black dot here is a non-zero, and for purposes of better visibility, I have just colored here the constraints belonging to this first subproblem, second, third, fourth. So we have 4 independent subproblems here, and they are only linked by some constraints saying that, well, what happens in these 4 subproblems, they together require a common budget or have to satisfy a common demand or something like this. Okay, and what we would do in the Dantzig-Wolfe reformulation is we would take these independent blocks, as we call them. Each of them represents a polyhedron, and we would reformulate each of them separately using the Dantzig-Wolfe reformulation. That would give me a pricing problem for each of these subproblems, and each and every one of them must report that the smallest reduced cost is non-negative, and then we would have reported optimality for the master problem. Okay, so often this leads to simplifications here, because often these subproblems are one and the same as for the cutting stock problem and also for the vertex coloring problem, and then we can, so to speak, solve only one representative for the many pricing problems. So we're only looking for independent set, not for independent set in each color, and this is often possible. I cannot tell you how this exactly works here, but I encourage you to read about that, and then you will see that often in your models you have that particular situation as well. Just to picture what we just did, because sometimes the picture says more than 1,000 words, as we know. So we have the master constraints here and the pricing constraints. So 2 different kinds of constraints, as we said. So the intersection of them gives us the feasible region of the linear program. And what column generation and for the Dantzig-Wolfe does is it reformulates one of these subsystems here, what we call the pricing problem, and it enumerates one after another the extreme points and extreme rays. So here on extreme points of that polyhedron, until we can prove that we have all that we need for proving optimality of the overall problem. And what we get them is, well, the feasible space again of the original problem where we started from? Yes, because that is an equivalent reformulation. So this is, imagine that was the LP relaxation of some integer program, and the reformulation is not tighter. So this gives me the same LP because it's an LP reformulation. Remember, if we had our examples, the pricing problems, they were not linear programs. These were integer programs, right? Okay, so what happens if the pricing problem is an integer program? That means these are the constraints of an integer program plus the requirement that the solution should be integer. So this is what is actually reformulated in this Dantzig-Wolfe formulation of an integer program. The polyhedron that is reformulated is the convex hull of all the integer points which are feasible for that subsystem of constraints dx greater than or equal to d here. Okay, then I have this convex hull here, and intersect that with the remaining constraints gives me a much tighter relaxation. This is why we are interested in this reformulation for integer programs, because it gives me potentially a tighter reformulation. Now, think about it, what we just did. We Dantzig-Wolfe reformulated a linear program, and this leads to an equivalent linear program is the claim here. So the question is that true? Is it false, or does it depend? So maybe we think about that. And if you have that, we can think about, okay, when the pricing problem is an integer program, would that reformulation lead to a stronger LP relaxation? That's always true, that's always false, or depends. So look at the picture again here, and then check what your answers are. So the answer to the first question is, of course, true. So this is what we repeated several times now. The Dantzig-Wolfe reformulation of a linear program is an equivalent reformulation always. Yes, that's true. And for the second, maybe you are tempted to say yes as well, because if you look at this picture here, the reformulation when the subproblem is an integer program and you solve over the convex hull of the integer feasible points here, this gives me a stronger relaxation. You are tempted to say that's true as well. But imagine that subproblem here was an integer polyhedron already. So the description of the pricing problem, the dx greater than or equal to d, has already extreme points which have integer coordinates. If that happens, then the convexification here, so to speak, does not bring an additional value. And in that case, it may happen, or it will happen in that case. I wanted to say it may happen that your pricing problem has this property. In that case, you would not gain anything from the reformulation. So the answer here is it depends. And it depends on the integrality property of the pricing problem, whether or not the LP formulation already gives you automatically an integer solution or not. Okay, so let's stop here for a moment and think what we did. So we said this column generation, as we've seen it in relation to the Dantzig-Wolfe reformulation, our ability to do this relies on the ability to being able to optimize over this set here, over the convex hull of the integer feasible points to, well, which are feasible to this reformulated constraints, the dx greater than or equal to d. So this is what we need for solving the linear programs as well, that we have this readily available. But for integer programs, we assume that we can obtain the integer feasible solutions or even integer optimal solutions for an IP here. And that gives us some hint how we could choose this set that we reformulate. So on the one hand, it should describe some structure, so that should be some problem where we think we can easily optimize over. And on the other hand, for helping the LP relaxation, that should be some set where actually the dual bound from the reformulation improves, so that the convexification of this of the integer feasible points for this set here actually gives us something stronger than the LP relaxation alone. Okay, so this should guide how we should select the subset, what should go into the pricing problem. Sometimes this is immediate, but sometimes this is a difficult problem to select, and it only helps to look into the literature to select a good pricing problem, so to speak. Let us look at an example, another one, which gives us some more light on this question here, hopefully. So what we would like to do is we are given this graph here, and the problem is taken from this primer and column generation. So this example here is in written. You can read this later on if you like. We are looking for a shortest path from this vertex 1 to the vertex 6 here, and we're given the cost on the arcs. But this is a resource constraint shortest path. So we have a second number here, which is the traversal time on each arc, the time it takes to go from the one point to the other one. And what we have as an additional constraint here is the total traversal time of the shortest path we would like to see from 1 to 6 should not exceed 14 time units. Okay, so this is the problem. It's a very simple one, but it appears as a subproblem in many, for example, routing applications, crew scheduling applications, and so forth. So here are some solutions. So here's one path, which is very, very costly, as you can see, but it is very quick. Here's another path which is very slow but is very cheap. Both is actually not what we want. What we want is this one here. So the time, it's not the quickest, but it's at least quick enough for the resource constraint here. And its cost is 13. And we can prove that this is an optimal path from 1 to 3 to 2 to 4 to 6. Okay, and how would we compute that? Here's an integer program. Of course, we're here for integer programs. We can model this problem as an integer problem, as a particular flow problem. So I have variables here on each arc, the amount of flow. So it will be always 1 unit of flow or no unit of flow on the arcs. So this is a binary variable actually. I will send 1 unit of flow starting in vertex 1. I will receive 1 unit of flow in the target vertex 6. And for all the other vertices, I have flow conservation. Okay, so this gives me sending 1 unit of flow from the source to the target node at minimum cost. And the additional constraint I have here is the resource constraint, summing the time it needs to traverse the entire path, and that should not exceed 14. We could solve that by branch and bound, of course, but we won't do, because we see there's a particular structure in this integer program here I have algorithms for. Because if I remove the resource constraint, I see, what remains is a shortest path problem, and I perfectly know how to solve shortest path problems. Can I exploit this knowledge that I have algorithms for solving shortest path problems? Okay, so if I drop the resource constraint, this is what remains. So this is what should go into the pricing problems, into the pricing problem, because we said these are the easy constraints. We said we have algorithms for that. So in that sense, these are easy constraints. Easy constraints. So this is a particular network flow problem. And remember from Dantzig-Wolfe, what we need to have access to is the extreme points of that polyhedron here and the extreme rays. So first of all, I can drop the integrality constraint here, because we know if we do so, the remaining linear description has the property that the extreme points are integer and there are no extreme rays here. So we can directly use this, the convex hull of these extreme point of the integer feasible solutions here, and that would give me a polyhedron with integer vertices. This is known from theory. Okay, what is also known from theory is that these extreme points, they are incidence vectors of paths, and every point within that polyhedron is an incidence vector of a flow from 1 to 6. And what this essentially says here is every flow, every arc flow is a convex combination of path flows from 1 to 6. So this is just a side remark, but we recognize this theoretical result from flow theory here in this reformulation. Okay, now let's do the Dantzig-Wolfe. Okay, Dantzig-Wolfe says, okay, every original variable value, which is a valid flow, can be expressed as a convex combination of the extreme points. The extreme points here are encoded in these xpij, which is for a certain extreme point, a path flow. We see whether the arc ij is on that path, yes or no. So this is a parameter here. These are variables for each path. So this means I'm convex combining the paths to build an arc flow. So this is what Dantzig-Wolfe formally would say, but this is how we could interpret this. And this has to be substituted in our original LP. So every xij can be expressed by this sum here. And now if you put the sum where an xij was before and rearrange terms a little bit, take your time to verify this. So just press pause to check that this is exactly where we should arrive. Then we see we have the reformulation here. We have the resource constraint as the single constraint in this master problem, and we have the objective function here. Okay, so then we can relax the integrality because we would like to solve that LP relaxation first. And if we do this, so you can see here, if we relax the integrality constraint, there is no need of projecting back to the x, so we can drop that constraint, and we would arrive at this problem here, which we call the master problem. And it has so many variables because it has a variable for every path in the network that we would need to solve that by column generation. So in this particular example, of course, it's only 9 variables, but if you have a larger graph, there would be many more paths, many more variables. So here I can write the entire master problem on that slide, but let's assume 9 variables is so absurdly too large that I cannot solve that I drop most of the variables, arriving at what we call the restricted master problem. It has a small subset of the variables only. Okay, and we add more variables only as needed. We do column generation. Question is how? So how would we generate or add a path variable to that model where which we don't have currently? And what we know is, well, when we solve the restricted master problem, we obtain a dual solution simultaneously. And for one specific variable, for example, for this one here, we can compute the reduced cost, which is always the same, the original cost minus the dual variable values times the coefficient column of the variable. Look here, the 9,1 is the coefficient column. Here's the convexity. No, that's not even the convexity. Here's the convexity constraint, and here's the cost. So for this particular column, that would be the reduced cost depending on the dual variable values. Okay, and in general, here's the formula. Again, I encourage you to pause and check that this is exactly the original cost minus the dual variable vector times the coefficient column. Here, there's only one coefficient in that column and 1 in the convexity constraint. So convince yourself that this is the correct reduced cost. And I'm interested in the smallest reduced cost, so I'm minimizing that function subject to the xij here, encode a feasible column. So what was a feasible column? It was a path from 1 to 6, and we know how to formulate that. Surprise, surprise, these are the constraints we have seen before in the reformulation. Well, that is no coincidence. This is how we did it. Okay, so look back again. Now we arrived here. And with your knowledge about Dantzig-Wolfe reformulation, check the previous slides again to see that this is the pricing problem minimizing the reduced cost over the substructure, which we recognized in the original model, which we said, oh, this is easy, this is a path. Now it reappears here as a path from 1 to 6 in the subproblem. This is exactly what we wanted. Now we can solve that one here. This is the pricing problem, and if the optimal objective function value is non-negative, we know there is no improving variable. And otherwise, the xij here will encode a path from 1 to 6, and that corresponds to a variable in the restricted master problem. We should add there and potentially have progress. Okay, so this is column generation. What is the pricing problem looking like? So we said that is the reduced cost over the solution is a path from 1 to 6. So again, this is a path from 1 to 6, so it's in this original network, a shortest path problem, but the cost is modified. So it's not only the original cost, but it's the reduced cost. Yes, you see here on every arc, check the formula again, it's the original cost minus the dual variable value times the coefficient in the variable column we are trying to generate. So this is exactly what the formula said. And now that you see this here is we solve a shortest path problem to solve the pricing problem. Let me repeat, this is the reason for the reformulation, because we thought we were able to solve shortest path problems easily. We did this reformulation, the decomposition, so that we can exploit the algorithms we have for solving shortest path problems. I would like to do this with you with this numerical example, and I would like to start in the beginning. We always said, okay, let's start with a small subset of the variables, but where do they come from? Initially I may have none, okay, and this sometimes happens, and that would in particular mean here, because of the convexity constraint, that I'm infeasible. So to be at least technically feasible, one possibility is to just add an artificial variable to the master problem. This happens often in the big M approach, and the big M means I have a huge penalty, well, 100 is huge here, for not using, so encouraging me not to use the artificial variable. This is how I could start. This is my initial restricted master problem. It does not contain any of the master variables at all. At least I can solve that with a, for example, simplex algorithm. I would get an objective function value of 100. Well, yes, I would use the artificial variable entirely as a huge cost, and I get the dual solution here. If you know something about duality and LP duality, you can pause here after we have done this example and check that these numbers actually make sense. So I get the dual solution, so I can formulate the objective function of the pricing problem and ask for a smallest reduced cost path from 1 to 6. And I get one. It's this path here, 1, 2, 4, 6. It has original cost 3, and it has a duration of 18, and this is its reduced cost. So you can see the original cost of the path minus the dual variable value times the coefficient in the column. So you can see that the numbers here are actually consistent with the formulas we have obtained. Now there is a negative reduced variable, so we add it to the restricted master problem and re-optimize. We get the new objective function value, a new solution, and so the solution is depicted here. So it's still not feasible for the original problem. It uses this path at a certain amount, but it cannot fully use it because it's too long. So in terms of time, it's 18 time units long. I can only use 14, so I cannot fully use this path. I still have to use the artificial variable here. And I also get a new dual solution. I formulate the pricing problem. Actually, only the objective function changes. Yeah. Then I solve the pricing problem, get a new path here of negative reduced cost. It is very costly, but very quick. And I add this to my restricted master problem and re-optimize. And then I will see, now I'm using both paths fractionally and not the artificial variable anymore. So now I have a feasible solution toward the original master problem at least. It's still costly, but I get a new dual solution here. I call the pricing problem with a new objective function. I get a new path. I add it to the restricted master problem. I re-optimize it. I get a new solution, and in particular a new dual solution. I use that to modify the objective function of the pricing problem, call the pricing problem, still a path of negative reduced cost. I add it, get a new solution to the, and then I finally, with this dual solution here to the final restricted master problem, I call the pricing problem again, and the smallest reduced cost is 0. So that means there is no negative reduced cost variable, and I stop. I have generated 4 out of 9 variables only. So in general, it's hopefully much less the fraction of the variables I actually generate. But I have solved the master problem to proven optimality now, and I can even project back to the original variables. So in the original terms, these are the arc flows, and this is visualized here in the graph. So this is my fractionally optimal solution to this problem. Some remarks. These are the paths we use. So these are the fractional values of the master variables. And you can see I even use paths in my solution which are infeasible to the master problem. Yes, this is not surprising because the master constraints were not respected when generating the paths. Okay. What is more important is that from the solution, so from the solution value here of the LP relaxation, I get a dual bound. Yes, of course. A dual bound, so a lower bound in this case on the optimal integer solution value. And that is in this case the same dual bound I would have obtained from the original LP reformulation for the model we started from on the first slide. Okay, and the question is, why is that the case? So do you know why we have this reformulation and we get a dual bound from the reformulation, and it's no better than the LP relaxation of the original formulation? We talked about that already. Well, because you may know, and I've talked about that already, the polyhedron describing a flow formulation is known to be integer. So all the extreme points of that flow polyhedron are integer extreme points, and that means, we have seen that in the Dantzig-Wolfe reformulation, we cannot gain anything in terms of the LP relaxation, so it's the same bound as the original LP relaxation. So that's bad, but at least it showed us how the column generation mechanism works. So here's the answer. We cannot improve when the pricing problem automatically has integer solution where we solve only the LP. Good, solving the LP, that's good, because this is all we did so far. So we said we used the Dantzig-Wolfe reformulation. Why? To obtain a stronger relaxation. So in the example we have just seen, the reformulation was not stronger, but for the first two examples it was. So for the cutting stock problem and the vertex coloring problem, the reformulations are stronger than the original LP relaxations. And you know other techniques, meanwhile, to strengthen an LP relaxation. So what you would usually do is to add cutting planes. And it would be nice if these two worlds would not be separate, but could benefit from each other. And actually, we can do this. So typically, we have a lot of cutting planes for the models in the original variables. Let's say for the coloring problem, or for the cutting stock, or vehicle routing. So there are a lot of cutting planes, and it would be nice to be able to use them. So what would happen if I have my model here, and let's assume I would like to solve that by a Dantzig-Wolfe reformulation, and I'm doing column generation, and the pricing problem is here over this X domain. Okay, so this is what we just did, and I'm trying to do the same, but this time I'm adding to my original model more valid inequalities that I know from the literature. The only thing I have to know is that these additional constraints, when I keep them in the master, let's say, they will be Dantzig-Wolfe formulated, and they will give additional dual variables. Okay, so in the master problem, all this looks exactly the same as these, as if they were just model constraints. I mean, after all, they are just feasible constraints. And the only thing that happens to the pricing problem is that this dual variables for the new constraints have to be respected in the objective function of the pricing problem, because the objective function measures the reduced cost, and the reduced cost is what is in the objective function of the pricing problem. But the domain of the pricing problem is not touched, because it's still the same constraints that go into the pricing problem. This is usually true. You can construct pathological examples where the pricing problem domain would also change, but in everything you will see, typically this will probably, yeah, let's say this will not happen, not in this hour here, where we discuss only the basics. Okay, so the objective function will change, and you know how, because we have the dual variable values, so you can just put these additional cuts from the literature into the master. So that means the column generation is compatible with cutting plane techniques, which is very good, because you have two techniques now to potentially strengthen the LP relaxation. If you do this, you will probably see that it does not really work. Why? Because the Dantzig-Wolfe reformulation, so empirically from our experiments, is so strong already that all the additional cutting planes that you can add from the literature typically don't help. Okay? They are typically already satisfied. So what we could do, because we have this reformulation thing, is we could try to find new cutting planes, which are formulated in the new variables we have in the master variables of the reformulation. Okay, so what sometimes happens is either because people use a certain variant of the Dantzig-Wolfe reformulation, which is called discretization, I won't talk about this here, or because they don't apply Dantzig-Wolfe reformulation at all, but directly formulate an integer master problem. This happens often in the literature. Then people try to directly find valid inequalities, cutting planes, on these master variables. Okay, so these did not arrive, let's assume, by a Dantzig-Wolfe reformulation. They also have dual variables, and they have to be respected in the pricing problem. The problem is, if you think about this here, is that I don't know exactly how to respect the dual variables in the pricing problem, because now my subproblem domain may be affected from these modifications I just did here. And because that would be too complicated to explain in theory, let's look at an example. It's again a graph coloring problem. This time we would like to color the edges. So we still have an undirected graph. We would like to color the edges. That means every edge must receive some color. And whenever two edges are adjacent, so they meet at the same vertex, they must not receive the same color. Okay? If you really try this yourself, a small graph, color the edges, and check the solution. So what we just did. This is what Nemhauser and Park did some 30 years ago, and they saw, okay, the solution, each color class is a matching in that graph. So a set of edges, no two of which coincide in one vertex. So this is a matching. Then you can take the set of all the matchings in a graph, okay, and have a binary variable for each of them. And all you need to ensure is that now you're selecting some of the matchings. And what you ensure is that every edge appears in at least one, or exactly one, doesn't really matter, one of the selected matchings. Every matching will have to be colored in a separate color afterwards. So you're minimizing the number of colors, which is the number of selected matchings to cover or partition the edge set of the graph. Just pause for a while and check that you understood that this model is right. It's a beautiful model by Nemhauser and Park. This is a model with a huge number of variables because it has a variable for every matching in the graph. It's huge. Okay, so you cannot solve that. Instead, you solve, when you solve the LP relaxation, you just start with a restricted master problem where you have a few variables corresponding to a few matchings. And this would be the pricing problem. So here is the formula for the reduced cost. It's again the original cost 1 minus a dual variable vector times, well, a coefficient column here. And the coefficient column is, it encodes in binary a subset of the edges. So that should be a matching, right? And because I have a constraint here for every edge in the model, I have a dual variable for every edge. And that goes perfectly well here in the objective function. So I'm summing over all the edges, the dual variable value obtained from solving the restricted master problem times, so to speak, the incidence vector of a matching. And we know how to formulate matchings. We will go there in a second. But let's look into the literature. What does it say about the edge coloring problem? And we would find this class of valid inequalities here, the odd circuit cuts, and this is how it works. So here you can see a subset of an edge coloring in the graph, right? So this is how it should look like. And here's a cycle of odd length. And what we can see here is how many colors will we need at least to color that odd cycle. And if you know a little bit about combinatorial optimization, you will immediately see that 2 colors will not do, because so you have 2 colors here, you have 2 colors, or the same color here, and then you will need a third color. You will need at least 3 colors to color an odd cycle. That means that from all the matchings we intersect in the graph, we would have a red edge matching here, a blue edge matching, and a magenta edge matching somewhere in the graph. And from all the matchings that intersect this circuit, so this odd cycle, and from all the matchings that intersect that cycle, we need to take at least 3. Okay, so this is what the picture said, and this is what the odd cycle cut, the odd circuit cut says. So from all the matchings I could select, I look at those matchings which intersect the cycle. So this is how you should read that here. And I should take at least 3. This is an inequality I can put to the master problem. Okay, now this inequality has an additional dual variable, and that has to be respected in the objective function of the pricing problem. Okay, here is the objective function, the original objective function of the pricing problem. And here is this additional dual variable for this cut. How would I try to respect it? Well, I have a new variable, which is a binary variable, and it says the matching I construct in the pricing problem, it intersects the odd cycle corresponding to the odd cycle inequality, yes or no. And if it does, then that matching would appear in the sum here with the 1 coefficient. And if it would appear with the 1 coefficient, it would mean that in the objective function, I would have to subtract the corresponding dual variable. So this is the good interpretation. Now we have to ensure that the variable y follows that interpretation. And here is a constraint. So this is ingenious work. So you shouldn't see that at once. I'm trying to explain this to you. So this is the y variable saying that the matching intersects that cycle. And here are the variables of all the edges in that cycle. Okay, and this means here the variable can be only one if I select at least one edge from the matching, from that in the matching from that cycle. And this is exactly what we need. And if you look at the numbers here, there is encouragement that the y actually gets to 1 whenever it can. So whenever I pick an edge in the matching from the cycle, the y variable will go to 1, and then we'll count the right coefficient, which is the dual variable value of the cut in the objective function, and then correctly computes the reduced cost of the new variable, of the new matching I produce in the pricing problem, respecting the dual variable of the cut. So that means we can formulate cuts directly on the master problem, but it may imply severe modifications in the pricing. As you see, sometimes it's possible, and then we may have the benefit that these cuts are actually stronger and really strengthen the LP relaxation we can obtain from the Dantzig-Wolfe reformulation or from the stronger column generation based formulation. Okay, now we are here with a stronger formulation, and what we still want to do is we would like to solve an integer program. And what we did so far is we only solved the LP relaxation. So that was only the first step. All we did so far, we have no integer feasible solution so far, right? And you know the algorithm for solving integer programs is the LP-based branch and cut algorithm. And what I would like to show you now is what the branch and price or branch price and cut algorithm is. It's just the algorithm you know, the LP-based branch and cut algorithm, where you solve the LP relaxation in every node of the tree, well, by column generation. And what we did so far is we solved the root node. We solved the very first LP. So here's how that goes, where that can be talked about rather quickly. So this is what we obtain from Dantzig-Wolfe reformulation of an integer program. We arrived here at this. You may recognize it as the master problem, and you can still here have the projection of the master solution back into the original variables. And what we wanted to have is integrality on these original variables. Okay, so this is where we arrived. This is an equivalent integer reformulation of the original model we want to solve. And now when we solve the LP relaxation of that one, we can look at this projection back into the original variable space. And it may be that this is already an integer solution. We may be lucky, then we are done. Okay, good. You know that this almost never happens. So there's at least one variable which has a fractional value. And again, variable here is an original variable projected from the master variables. Now, what we would do in branching is we create two branches. Well, we round down the value of the variable in one branch, and we round up the variable value in the other branch. So we get two new subproblems, just as in branch and bound. And so that should work exactly the same as you know it, except that you somehow have to enforce these branching constraints now in the reformulation. And there are two ways of doing this. Let's look at both of them. So I will only look at the down branch. So where we impose that there's an upper bound, so the current value rounded down, on a currently fractional variable in the original space. Okay. If we would have this constraint here in the original problem we would like to solve, we would arrive at this constraint here in the master. Think about this. This is just a constraint. We do the Dantzig-Wolfe reformulation. We arrive at a constraint, this one here. This is summing over all the extreme points and all the extreme rays with the corresponding coefficient of the extreme points and the extreme rays in the ith component, which is the ith variable which was fractional. And that should be less than or equal the current value rounded down. So this is just this branching constraint reformulated in the master. Good. This gives an additional dual variable, but we know how to respect that in the pricing problem, because then this is exactly like handling cuts in the original master in the original problem. Just as we have seen, the pricing problem does not change. It's still the same domain. It's only the objective function that changes, but we know how. There's this variable here which is affected with this additional constraint variable coming from the dual variable value of the branching constraint here. So we know how to do this already. This is one way. You could directly enforce the branching constraint in the pricing instead. So meaning that you directly change the pricing problem domain. Now the objective function would stay the same. So meaning that you will not generate any variables which violate the branching decision. Okay, so no new variables which are not consistent with branching, but old ones in which you still already have in your master problem could contradict the branching decision. So you would have to remove all these variables from the restricted master problem, and you would not really physically remove them, but you would put local bounds in the node to fix these variables to 0. And you can also do a combination. And the question is then, well, what should I do? Should I put the branching constraint in the master, or should I do this in the pricing? And theory says, well, you put this in the pricing. Why? Because it's stronger. Because if whatever you put in the pricing problem, it will be convexified, because we are solving the pricing problem in integers, right? And this is potentially stronger than just respecting the constraint in the LP relaxation. So this is what the theory says. It may happen though that this is harder than in your pricing problem. Typically it's not, and it's often enough we solve the pricing problem as an integer program anyway, so putting a bound on the variables there is not so bad. But it may change your pricing problem, and your combinatorial algorithm that you might have to solve it might no longer work. And there are more reasons for that we haven't talked about, which would speak for putting the branching constraints in the pricing problem. You may, if you just pause and think about that, so okay, that is what we were interested in, integer solutions to the original model, but we could branch on the master variables as well, right? So why didn't we do that? So we could look at the master solution. It may be fractional, and we could branch on the variables. This may be wrong, in particular, because no one so far typically forced us that the master variables should be integers. Often enough they are, in particular when we are looking at binary programs. Some people directly formulate integer master problems, and then this is okay. But sometimes there are problems, in particular when we arrive at a reformulation with Dantzig-Wolfe, just as we did it, that may be wrong. But worse, the result is unsatisfactory. So the tree is typically very unbalanced. If you forbid a certain configuration, a certain cutting patterns, that means that there are many alternatives. So this typically does not do anything to the bound. Whereas if you enforce a certain cutting pattern, for example, this has a huge impact potentially on the bound. So that will be very different branching decisions, and this is unwanted in branch and bound. and you don't know how to respect a forbidden certain configuration in your pricing problem, because the pricing problem must be forbidden to regenerate that particular configuration that you have forbidden. And typically this is not so easy to do. So we would not branch on the master variables unless there are certain branching rules which exploit certain strategies and certain problem structure, and they branch also on combinations of master variables, but we will not talk about this here. Look at the example instead that we have seen so far, how the branching on the original variables could look like. So we look at this resource constraint shortest path example, and the solution again, what we did so far is we solved the root node of the branch and price tree, and it's fractional in the original variables, as we can see. So here's the fractional flow on the arcs, right? So we can branch on these fractional arc flow variables. So we have, for example, from 1 to 2, there's a flow of 0.8, should be integer, should be 0 or 1 or larger, but integers. So we have the two options. We can put the branching constraint. So let's only consider here the branch where we down branch on that variable. So we will not use the arc. In the pricing problem, it's easy. We could just remove that arc, so we can no longer use it. And in the master problem, or in the restricted master problem, we would have to eliminate all the paths that use that arc, so that we can no longer use it. These are these two variables we have generated so far. And then we would be infeasible in this case and would regenerate paths which use the 1,3 arc. So this is what would happen in the next node of the tree. And the other branch, on the other hand, is when we enforce that arc, we can also do this in the pricing problem by eliminating all the edges or the arcs leaving vertex 1 and entering vertex 2. So this is what's happening here. So that enforces in a certain way usage of the arc 1, 2. This is what we want. So this is how to reflect this in the pricing problem. And we would have to eliminate all the paths which use either one of these two arcs from the master problem, so that they are not used in the AP relaxation there. So this is how branching on the original variables could look like, and I can even, when I use a combinatorial algorithm, sometimes respect that decision in the pricing problem. Okay, much more would there be to talk about when it comes to branching. What you should keep in mind is that often for your problems, branching on the original variables works. So in fact, it always works if you don't do any fancy stuff like aggregation or stuff. Okay, if you do, then it may no longer work, and then you may have to resort to certain other rules. Often enough then, because you have some kind of assignment problems in your original model, and that remains in the master. This is often the case in vehicle routing, in bin packing, in the generalized assignment problem, in vertex coloring, in edge coloring. So in many problems, you have set partitioning master problems. And for that case, you should check the Ryan and Foster branching rule, which often works in practice, and where there's also a skip example where you can look how this is implemented. Okay, we are almost done. We're done with what we should have done. It's way too long right now, but still I have something that we could look at, which is the dual point of view. And there is also a lot to say here. And all that has somehow to do with Lagrangian relaxation. But at least I would like you to know that this exists, so you can read about it and hopefully speed up your code sometimes. So this is the Dantzig-Wolfe master problem. So check the slides how we arrived here. We had these variables corresponding to extreme points of a certain polyhedron we reformulated, and variables corresponding to extreme rays. We have the master constraints here. We have the convexity constraint. This is a linear program, the Dantzig-Wolfe master. We can not solve that one, but we can solve the restricted version of it and obtain dual variables. So what if we directly consider the dual here? So this is, well, the dual of the master problem. It has a constraint for every extreme point and a constraint for every extreme ray. Yes, this is what duality tells us. You can see here on the right hand side the cost coefficients. and on the objective function, the dual variables appear with the right-hand sides of the primal, and it's a maximization problem. So if we look at this here, you can see the relation that a negative reduced cost variable in the primal is nothing else but a violated constraint in the dual. This may not surprise you, but what we should keep in mind is if we add variables to the primal, we add rows, constraints, to the dual. So column generation is row generation in the dual. Good. Why is this of importance? Because there is something that is called Lagrangian relaxation, and it works not for solving an integer program, what we are interested in, but Lagrangian relaxation is a method to obtain hopefully strong dual bounds. Okay, how does it work? It again splits the set of constraints into two. Again, they say, okay, there are some complicating constraints, ax greater than or equal to b, and the easy ones. And what we do is we relax the complicating constraints. What remains is an easy to solve problem, hopefully even in integers, but relaxing the constraints totally, entirely, maybe would give a too loose relaxation. I would lose too much structure. Instead, what I do, I keep them, the constraints, but only as a penalty when they are violated in the objective function. Okay, so I keep the easy constraints, I keep integrality, I keep the original objective function, and I keep a term that penalizes the violation of the complicated constraints. We don't have too much time to spend here. Maybe you press pause and look that this gives actually a dual bound, a relaxation value, a lower bound on the optimal objective function value I'm interested in for every non-negative penalty vector here for the pi. Okay. Now, when there is a lower bound for every pi, of course, I'm greedy. I'm interested in the largest and the best, such what we call the Lagrangian bound. So I'm maximizing over all the non-negative pi. So I'm maximizing this expression here. And we won't do this here, but a lot is known about this maximization problem. A lot is known about the Lagrangian dual function, which is reflected here in this L of pi function and so forth. It has a lot of nice property, in particular allowing us to apply a very, very simple algorithm, the subgradient algorithm, not to exactly maximize it, but to approximate a maximum. So we can, from many, many papers in the operations research literature, can obtain a best or closest to best Lagrangian dual bound on the integer optimum I'm interested in. Why am I spending time on this? Because I would like to revisit what we did in the Dantzig-Wolfe. Okay, because here is what the Lagrangian dual function looks like. And if we rearrange terms a little bit, so just press pause and take your time to check that this is a correct rearrangement here, is what we arrive at is the dual objective function value plus, and if you look at this here, this is how our pricing problem looks like. We are minimizing in integers over this set of constraints. This is what we reformulated in Dantzig-Wolfe, and the objective function is precisely the reduced cost measure of a solution in X. So this is what we solve all the time. We have the dual objective function value of the restricted master problem, which is by strong duality the same as the primal objective function value of the restricted master, plus the objective function value of the pricing problem. So that means we cannot help it. Whatever we do, when we do column generation, we solve that expression here as well, right? So we always obtain this Lagrangian bound for the dual variables coming out of the master problem. They are non-negative in this particular setting here. So we always obtain this Lagrangian bound, and we can plot this. So this is what you would see. This is the typical behavior when minimizing and doing column generation, how the restricted master problem objective function value develops. In the beginning, you have good progress, and then there is slower and slower and slower progress. So this is called the tailing off effect. And to mitigate that effect, you can monitor the dual bound, right? So you see, this is not monotone, but you get it for free. So this is the blue the blue dual function here, so the Lagrangian dual function. And the maximum of all these you have obtained so far, of course, is a valid lower bound. And when you say so, the absolute or relative gap or whatever between the restricted master problem and this dual bound is small enough, you just stop column generation. Here it looks very bad actually, so the gap closes very late. Maybe it closes earlier. Maybe you say, okay, 10% duality gap is enough. What I do is I stop column generation here. I have a valid dual bound, so I can start branch and bound. I just do it. I have a fractional solution. I just branch. Okay, so this may avoid a lot of costly pricing iterations here, and this is why having a dual bound available is very nice. Theory says that the two bounds, so the restricted master problem objective function value and the Lagrangian dual function, that they finally meet in the optimum. So this is what we mean when we say Lagrangian relaxation and Dantzig-Wolfe reformulation are equivalent. They give me the same dual bound. And what we also know is that the optimal dual solution from the master problem is a maximizer for the Lagrangian dual function. This is what theory tells us. And we can even see this in our example that it could potentially help. So this is the table we have seen so far when we solved the resource constraint shortest path master problem by column generation. This is where we arrived. And if you look at this second to last line here, if you look at the objective function value of the restricted master problem, which is 9, and the optimal objective function value of the pricing problem, which is minus 2.5, if we add these two, you get 6.5. So this is a valid bound on the integer optimal objective function. And because we know that the integer objective function value, the optimal one, will be an integer, we can even round up and receive as a dual bound, as a lower bound on the optimal integer solution value of 7. So already here without, so we obtain even the same bound, the same dual bound, even without having performed the last pricing iteration. So this is just symbolic here, but we have saved at least 1/5 of all the iterations. And in practice, this can be quite some time saver if you stop column generation when the dual bound is sufficiently close to the restricted master problem objective function value. Very nice. Okay, so that was quite some material. If you would like to dig yourself into this column generation, Dantzig-Wolfe, branch and price, branch and cut and price, well, we wrote quite something. We are, of course, or unfortunately, depending on your view, not the only ones who wrote about this. So you will find a lot of literature on that. So I would suggest to take a paper on your favorite problem. You know very well something about it, and then I'm quite sure that someone has tried a branch and price approach already. Then you can check that just to learn how it works. Or if you would like to do branch and price for a problem you have no one has solved so far with the branch and price algorithm, I would look into some similar literature and see how people address that. There are many tricks. I have tried to list some of them here, and maybe this slide is the only thing you will consider later once you have tried a branch and price implementation yourself. So number one advice is do not solve the pricing problem exactly, right? Because typically this is the most costliest step. So use a heuristic if you can. Try to generate more than one solution in the pricing problem if you can. However, you can generate cheaply columns that will always help you before you start solving the pricing problem exactly. Number two advice is avoid solving the pricing problem exactly. And number 3 is the same. And number 10 is the same. So this is really key. If you try to solve the pricing problem exactly in every iteration and only generate one column, you will probably never finish. So try heuristics. This is very important. Of course, when you're interested in the proof of optimality, in the end, once you have to solve the pricing problem exactly. But when you're lucky, only once. Okay, if you have many pricing problems, and that happens in applications a lot, do not solve all of them for the same reasons. It's all costly. Typically, all of them respond to the same dual variable values of the master problem. So typically, in the next iteration, you will not use all the columns coming from all the pricing problems. So don't call all the pricing problems. As we've just seen, monitor the Lagrangian dual bound. You get it for free. So when the duality gap is small, just branch. Try to get integer solutions quickly. When the master problem is hard to solve because I don't know, you need an interior point method or the simplex method or whatever method to solve them. Well, it's a linear program, right? You can try to steal a bit in the Lagrangian literature. You could also alternatively get a new dual solution, not by solving a linear program, the restricted master problem, but doing some of these subgradient iterations. There's also literature. I will link you in the comments of the video, and you will find many more techniques like dual stabilization, cutting planes, and all that. So all that may be relevant, but need not be relevant. So in the end, only experimentation will tell you whether it's actually worth trying to do this implementation. And in the exercises, we will see at least some way of using a very generic branch and price solver to at least evaluate the potential whether your problem you're trying to solve could be better solved by branch and price. So that will be the GCG solver that hopefully gives you some, well, let's say, intuition whether a fully fledged branch and price implementation will pay or not. So this is my last slide. Usually what we do in operations research and in computational optimization, when we try to solve practical optimization problems, well, we have the problem, then we try to formulate a model, then we pick an algorithm. Typically the algorithm is LP branch based branch and bound, and then we implement it, and often enough we don't have to implement it because it's already implemented by someone. And this column generation and branch and price somehow mixes the second and third steps, so model and algorithm. So you can really try to modify the algorithm so that it fits your model better. Well, that works for branch and bound and branch and cut as well. But what the branch and price and column generation world additionally gives us is that we dare to model, well, in different variables maybe we wouldn't have tried before. All these configurations, the combinations, the subsets, the selections, the sequences we have seen, for example, for the problems we've seen, we model in paths, not only in arcs. We model in entire matchings, not in edges. We model in entire patterns to cut, not only in single orders. So we model in larger parts of a solution, and this is only possible because we have that column generation algorithm available. So I hope, of course, that you will try it one day, and if you do, never hesitate to contact us and contact me in particular. That was much longer than we were allowed to use for this unit here, but we had 3 topics to cover on that decomposition day, so maybe you do not have to digest everything at once. Maybe you can save something for later. I hope you liked it. We will meet in the exercises. Until then, stay safe and enjoy the rest of the CO at Work course 2020. Bye-bye.